Hello, everyone. My name is Mina. I am a PhD candidate in the Electrical Engineering Department, working with Professor Grace Gao at Stanford University. And today I'll be presenting our work on performing continuous GPS authentication with the Chimera signal enhancement using stochastic reachability analysis. So because currently GPS signals are unencrypted and have publicly available signal structures, all civilian GPS users are vulnerable to spoofing attacks. So as a result, the Air Force Research Lab has proposed the CHIPS Message Robust Authentication Signal Enhancement for GPS L1C, and that's going to be tested on NTS3, and it'll cryptographically sign both the data and the pilot channels of the L1C signal. So users who only have access to the GPS L1C signal, they can receive the slow channel encryption key every 3 minutes. Whereas users with access to the secure out-of-band channels, they'll receive the fast channel encryption key every 6 seconds. However, in either case, the Chimera authentication ability is not continuously available, so even fast channel users will experience a 6-second latency in their signal authentication, whereas for moving receivers, typically GPS measurements are received at a much faster rate. So we want to develop an approach to validate our GPS signal between these Chimera authentication times. And there's been significant prior work to conduct spoofing detection by checking that the GPS signal is consistent with a self-contained sensor like an IMU or a speedometer. And oftentimes these methods assume perfect sensor calibration or a zero mean Gaussian noise model. However, these sensors and even GPS in practice, they might contain unknown biases, which might be difficult to calibrate perfectly, especially when less expensive sensors are used to reduce costs. So for example, IMU biases vary with time, and even due to changes in the environment like temperature and humidity. And for odometers, biases can occur through wheel slipping, and oftentimes the standards for the accuracy of odometers and speedometers, it's specified in terms of a % bias range. So as a result, we wanted to develop a more general consistency checking spoofing detection framework, which can handle both bounded biases and stochastic uncertainties. So in this work, we derive a state estimator and spoofing detector to perform continuous GPS signal verification and conservative state estimation between the Chimera authentication times. So we want our detector to leverage the previous Chimera authenticated GPS solution and for the derivations to apply to any general self-contained sensor. And we also derive our estimator and detector to account for unknown bounded sensor biases and stochastic uncertainties. And correspondingly, we give a probabilistic overbound on the spoofing statistic and the set of vehicle states during the authentic conditions, which then guarantees that we can satisfy the user-defined false alarm rate. And finally, we probabilistically validate that we satisfy this false alarm rate in the presence of unknown bounded sensor biases and stochastic uncertainties. So first, I'll go over some preliminary details regarding stochastic reachability and probabilistic zonotopes. Then I'll go through the details of our proposed stochastic reachability filter and spoofing detector. And finally, I'll present our experimental validation results and summarize this work. So to give some background, stochastic reachability is a fundamental approach to model state uncertainty. So for example, with Kalman filtering, we model the state uncertainty as a Gaussian probability distribution over the state. So given an initial distribution and an input distribution, we can represent the distribution over the propagated state. And for classical reachability, we can instead maintain a compact set of possible states. So from an initial set of states and a set of inputs, we can model the reachable set of states. And this allows us to model how the state evolves in the presence of bounded uncertainties. And finally, with stochastic reachability, this is an extension of classical reachability. So we maintain a stochastic set of possible states or a probabilistic overbound over the state space. And this allows us to model the state in both uncertainties that have bounded biases as well as stochastic uncertainties. So probabilistic zonotopes are a fundamental mathematical object which allows for this stochastic set representation. So these objects, they model the enclosing probabilistic hull or an over approximation of a set of probability distributions. And they can provide an envelope for a arbitrary set of uncertain distributions, or they can be interpreted as encompassing a set of Gaussian distributions with some uncertain bounded mean. And then we use this latter interpretation in this work. So we can define a probabilistic zonotope with 3 parameters, a center point C, width G, which reflects the uncertain bounded mean, and then the covariance sigma, which is reflected in the tail of the probabilistic zonotope, and that models additional stochastic uncertainties. And a nice property of these probabilistic zonotopes is that they're closed under linear maps and Minkowski sum operations or set summation operations. So now I'll go over our proposed stochastic reachability filter and spoofing detector. I'll first describe our problem statement and give an intuitive understanding of how our technique works. Then I'll give an overview of the state estimation system and modeling assumptions. And then I'll finally describe how we compute the stochastic reachable set of state estimation errors and how we derive our stochastic reachability spoofing detector. So consider we have a moving vehicle. It uses the fast Chimera channel to authenticate every 6 seconds. And in addition to the GPS receiver, it has on board a local self-contained sensor. So during this Chimera epoch, the receiver obtains GPS signal measurements, but they have not yet been authenticated. So we can model a probabilistic zonotope of the vehicle state using the previous Chimera-authenticated GPS measurement as well as the measurements from the self-contained sensor. And then similarly, we can model a probabilistic zonotope over the vehicle state from the unauthenticated GPS measurements, as well as the variance and bounded biases under authentic conditions. And at the same time, if we trust our received GPS, we can model a tighter probabilistic zonotope over the vehicle state by fusing these 2 sensor measurements. So intuitively, the difference between the GPS only and the self-contained sensor only state estimate should be small, and then these orange and blue probabilistic zonotopes should have significant overlap if the signal is authentic. However, we formally derive a spoofing detector with a probabilistic overbound of the spoofing statistic under authentic conditions. So if the probability of the expected error is high, then the received signal is likely authentic. Otherwise, if it's low, then we can determine the received signal to be likely spoofed. And then we have a binary spoofing decision with respect to a user-defined false alarm requirement. So in the case that the detector outputs an authentic decision, we use the fused state estimator and probabilistic zonotope. Otherwise, if the detector outputs a spoof decision, then we rely on the self-contained sensor information until we can re-authenticate our GPS signal with Chimera. So we design our stochastic reachability filter and spoofing detector by extending a Kalman filter-based estimator. So it propagates a probabilistic zonotope instead of a zero mean Gaussian distribution. This is similar to prior work in our lab. And we model the state propagation using the self-contained sensor measurements, so like an IMU or speedometer. And the forward propagation model F is shown here. So it takes in the state X, the sensor input U, and the propagation noise W. And then we perform measurement updates using the unauthenticated GPS measurement, which is here denoted as Z, and we have the matrix model H and the measurement noise R. And then we assume that we have models on the error probabilistic zonotopes over the propagation noise, as well as the GPS positioning measurements during nominal unspoofed conditions. And for this fused stochastic reachability filter, which combines both the self-contained and unauthenticated GPS measurements, we have to derive the state estimation error probabilistic zonotope. So the state estimate error is shown here, and it's the estimated state minus the true state. And we first derive a recursive expression of the state estimation error by using the standard extended Kalman filter expressions, as well as our system propagation and measurement models. So to get this expression, we linearize the dynamics with respect to the state estimate. And so we include a term here, L, that's shown in light green, to account for this linearization error. And we can see that this recursive expression, it represents the state estimation error in terms of 4 key terms. So the previous state estimation error, the process noise, the measurement noise, and the linearization error term. And then finally, to convert this to set notation, we replace those 4 point value terms with set value terms. So given that these terms are independent, we can perform Minkowski summation or a set summation over all 4 to obtain a recursive expression of the state estimation error probabilistic zonotope. And this is what is output by the fused stochastic reachability filter. And we can do a very similar derivation with the stochastic reachability filter based on the self-contained sensor information. So similar to the previous slide, we can again write the state estimation error and then derive a recursive expression. So the self superscript here is used to differentiate this estimate and error with those of the fused filter. And then we can see that this expression is much simpler in this case because we don't do a GPS measurement update to fuse the two sensor information. So in this case, the recursive state estimation error depends only on the onboard sensor errors and the linearization errors. And finally, we can go over the stochastic reachability spoofing detector. So our spoofing statistic Q, we consider the difference between the state estimate from the self-contained sensor and the GPS position measurement. So for both terms, we can represent the estimate in terms of the true position and the estimation error. And then correspondingly, we can simplify this to just be the difference in the estimated errors. So as a result, if we assume that the errors between these two sensors are independent, then we can model the stochastic set of the spoofing statistic during nominal conditions. And it's the Minkowski sum between the error probabilistic zonotopes. So we model the error of the probabilistic zonotope from GPS according to the variance and bounded biases of the positioning measurements under nominal unspoofed conditions. And then for the error probabilistic zonotope from the self-contained sensor, we can use the expressions derived on the previous slide for that corresponding stochastic reachability filter. And then finally, for our spoofing decision, we evaluate the probabilistic zonotope script Q at our point for our spoofing statistic, lowercase q. And then we check whether this conservative probability value exceeds our false alarm requirements. So if the probability of the spoofing statistic is sufficiently large, then we declare that this signal is likely authentic. Otherwise, we declare that it's likely spoofed due to the inconsistency between the GPS and self-contained sensor measurements. So now I'll describe our experimental validation setup and results. So we perform 1,000 Monte Carlo simulations in order to probabilistically validate those probabilistic bounds that we derived for our spoofing detector. So we set the false alarm threshold to 3/1000ths, and that corresponds to a 3 sigma confidence level. And then we see whether the maximum false alarm rate is in fact met during the authentic conditions. And then at the same time, we quantify the misdetection rate over the Monte Carlo simulations during the simulated trajectory drifting spoofing scenarios. And we also examine how the probabilistic bounds derive for our vehicle state. And for reference, we also we compute this result with the naively fused stochastic reachability filter. So that always outputs a fused estimate, and this helps us see how our Chimera filter is switching between the fused estimate and the self-contained sensor estimate. And then we also use the Cora toolbox to perform stochastic reachability analysis and the operations on probabilistic zonotopes for our method. And we perform Monte Carlo simulations on a ground vehicle model in 2 scenarios. So the first is a double integrator system, which has linear dynamics. We model the 2D acceleration, the 2D inertial frame acceleration inputs, and the propagation noise has bounded biases and covariance Q. And then we model the nominal GPS positioning measurements with a bias range of plus or minus 0.5 meters and a standard deviation of 5 meters in each dimension. So the second scenario, we use a IMU sensor model for the self-contained sensor. So because the acceleration measurements are now in body frame, along with those yaw rate measurements, the system has nonlinear dynamics, and we can model the vehicle trajectory using Portic splines. That ensures that we have a smooth trajectory. And then for the bounds on the IMU biases, we use typical dynamic bias ranges that are documented for consumer grade IMUs. And then we model the variances according to the root power spectral density values from the datasheet of an automotive MEMS IMU. Okay, so here we show the results for the double integrator system during nominal unspoofed conditions. We see the bird's eye view of the trajectory on the left with that corresponding 3 sigma error zonotopes for the self-contained sensor estimate in blue, the GPS position estimate in orange, and the Chimera filter estimate in green. So qualitatively, we can see that we have significant overlap between these confidence level zonotopes for the self-contained and GPS sensor. And because the detector recognizes that this received signal is authentic, the Chimera filter outputs the fused state estimate probabilistic zonotope, and we can see that the confidence level zonotope in green is much tighter than either of the 2 sensors individually. And we can see in the top right that the correct authentication rate in violet is consistently above the minimum required 3 sigma confidence level threshold. So that validates that we don't exceed the maximum allowable false alarm threshold of 3 1,000ths. And we also see in the bottom right that the percent of states that are bounded by the 3 sigma confidence level zonotopes for the proposed Chimera filter, as well as the naively fused filter for reference. And we see that both of these filters bound the state in all Monte Carlo runs, which is what we expect, since in this authentic scenario, the Chimera filter will nearly always output the fused state estimate. And now we have the results for a simulated spoofing scenario. So here we see the spoof GPS estimate deviates from the true trajectory, and then correspondingly, we can see in the top right that the misdetection rate is initially quite high, while the spoof GPS biases are small. However, as the GPS estimate deviates from the true trajectory, the correct detection rate increases and reaches a final value of 1. And then in the lower right plot, we see that the Chimera stochastic reachability filter nearly always bounds the vehicle state across the Monte Carlo simulation, whereas the naively fused sensor starts to fail to bound once the GPS estimates deviate from the true trajectory. And this is happening with the Chimera stochastic reachability filter. It's always bounding because it recognizes a spoofing attack and then switches to the self-contained sensor filter until it can re-authenticate the received GPS signal. Now we show the results for the IMU sensor system during authentic conditions. So we can again qualitatively see that we have significant overlap between the 3 sigma confidence level zonotopes for the zonotopes for the stochastic reachability filter for the self-contained sensor and then for the GPS sensor. So because the GPS signal is authentic, the Chimera stochastic reachability filter outputs the fused state estimate probabilistic zonotope, and we see that the corresponding confidence level zonotope in green is much smaller than either of the 2 sensors. And then in the top right, the correct authentication rate in violet, which is computed in 1,000 Monte Carlo simulations, that is consistently above the minimum required 3 sigma threshold. And then in the bottom right, we can again see that the both filters bound the vehicle state in all Monte Carlo runs, since the Chimera stochastic reachability filter nearly always outputs the fused state estimate for this authentic case. And now in a simulated spoofing scenario for the same system, we can again see that the misdetection rate is initially quite high, while those spoof GPS biases are small. And again, as the GPS estimate deviates from the true trajectory, the correct detection rate increases and reaches a final value of 1. And again, in the lower right plot, we can see that the Chimera stochastic reachability filter in violet nearly always bounds the vehicle state across the spoofing scenario simulation, while the naively fused filter starts to fail to bound. And this shows where our stochastic reachability filter is switching to the self-contained sensor information. So to summarize, in this work, we derived a stochastic reachability-based state estimator and spoofing detector in order to perform continuous GPS signal verification and conservative state estimation between the Chimera authentication times. So we derived our detector to apply for any self-contained sensor while relaxing the zero mean Gaussian distribution assumption to account for bounded sensor biases and stochastic uncertainties. And correspondingly, our detector provides a probabilistic overbound on the spoofing statistic, as well as the set of vehicle states during authentic conditions, thereby guaranteeing that we can satisfy a user-defined false alarm rate. And then we probabilistically validated that our derived probabilistic zonotope over the 1,000 Monte Carlo simulations, that it satisfies the maximum false alarm rate. And it also was able to detect spoofing once the trajectory deviates beyond the self-contained sensor errors. And we also demonstrated that the Chimera filter successfully probabilistically bounded the vehicle state during both authentic and spoofing conditions. So we'd like to thank Akshay Shetty and Shubh Gupta for the insightful discussions, as well as for reviewing this paper. And we'd also like to thank the Kirtland Air Force Research Lab and the National Science Foundation for supporting this research work. Thank you, and please feel free to leave any questions in the comment box.